Okay, we're gonna start. So hi everyone, welcome and thank you for joining DataCon LA 2020. I am Tala Ghazaleh, your host, and your co-host today is Ed Choi. We will be moderating the chat and the Q&A for you during this session. I am very excited to welcome you to the Emerging Tech track. Our talk today is Data Migration Lessons from the Trenches with our guest speaker, Nuri Halperin. Nuri is a senior architect focusing on data-centric systems. He is a MongoDB master and author of instructional online courses on pluralsight.com and a Microsoft MVP alum. Nuri is a frequent speaker at tech events and conferences, in person and lately, for sure, virtually. He is involved in the software community. He is involved in the software community, and he coaches youth robotics and contributes to OSS projects. Please help me in welcoming Nuri Halperin. Nuri, the virtual stage is yours.
Thank you, Tala. Thank you, everybody, for joining. Today, I'll be talking about lessons learned from a large data migration project of recent. It will involve some expectations and things we learned from the past, how we went from here to there, and lessons learned along the way. So it's a journey along a quite a large scale project. I'll talk a little bit about the challenges later. Large scale doesn't always mean too many bytes. It sometimes means too much traffic. It might sometimes means just too short of time. So we'll talk about some of these. Some of the experiences, I'm sure, are parallel to anything you encountered if you've ever done migrations. This is a heterogeneous migration, so the source and destination databases were not the same. Therefore, uh, we had to adapt along the way and figure out what's right for this project. So can't really do autopilot. Um, so in the beginning, the first thing we had to do is kind of adjust our head. I led a team that was in charge of the NoSQL. And besides that, we were focused on, in this talk, I'll be talking about MongoDB data sources that we ended up migrating mostly to DocumentDB and AWS. And the initial head adjustment was that um, depending on your experience, I've certainly been anywhere from software architect and CTO to just another line producer working on something very small and specific. And we had to adjust our head because we didn't own the whole project, right? We were just a part of a very uh, small part of a bigger project, which was to move the data. So from a perspective of the client, from a high level perspective, all they really cared about is the classic stuff of time, quality, budget. We had to fit this into a larger project, and we had to fit our sub part of the project into the time, quality, and budget that they allocated to us, plus minus some negotiation. But taking this client perspective is from their perspective, it's just move it. We're just a moving company. We take the stuff from here, we put it there. You want it in your new house. You want it spread a little differently because it's heterogeneous, not a homogeneous migration. But all in all, they don't want to get involved in the gory details. So we had to operate as an autonomous unit, providing the service upward towards the rest of the project. So with that in mind, we had to start breaking it into manageable, usable distinctions within the project. So we had to define the target and the ETL, the transformations necessary. If there were any around the schema or data or anything, we had to discover all of that. Then we'd have to provision things because we're going from on bare metal to cloud. We had to provision the right resources anywhere around networking, security, and finally the right sizing of the targets. As well as we would need to at some point test, make sure that what we're doing is good, and finally do a migration. And that's kind of linear, straightforward. In fact, if we laid it out, this seems fairly reasonable. We'd have to figure out what we're doing first, define where we're going and what needs to happen, provision it, come up with the resources, make sure it happens, build out the target database, and then take some workloads, test them against what we just provisioned, and finally do a migration. But even here, you see a little chicken and eggish kind of stuff because in order to do a migration, we would need some workloads. We need to test workloads after we migrated. So we have to uh, do some stuff in order to ensure we have data and we have ways to validate or qualify that what we're doing will work. So even those choices go all the way back to the definition where we weren't always sure that absolutely everything we're going to do is going to work with respect to the client's specific problems and specific workload, how they work with their data. So in fact, we exploded this simply simple 4-part view into a more granular view where our definition and provisioning is certainly are front loaded. We'd have to come up with something, and I'll talk about define in the next slide. But we'd have to generate and gather some sample data. We were not allowed to touch production data in some of the areas due to regulatory and internal company policies. We'd have to come up with tooling and how to do the whole thing. And do we have tools? Do we have to write their own and stuff like that? Test the workloads that the client has, not what we know from the past with regards to how this DBAS works. So this is all custom work. Um, we'll have to tune so that it does work with this workload, and then do migration with real data, test and validate in short amount of time, and then tune and debug post-migration if we need to. But so as we dug deeper and deeper, we got more granular with our taskification of all of these items and figuring out, giving them names and assigning them a time and people to perform. So the first step, getting started, and it can become quite daunting, very detailed. There's a lot of stuff you have to do in data migration, a lot of factors to take care of. It's not enough to just say, oh, I have Mongo and this is like the Mongo wire protocol. You have to dig in and understand exactly what is in use and how it's in use and by whom. You'd have to come up with counts. You'd have to see what is within best practices and what kind of breaks best practices, because those are the areas where it's likely exposing you to more risk during the migration. So a lot of details. And I would say the lesson one there was that we did not get all information in the format we requested. And that's not because we didn't work with good people. It's because there was a lot of information requested. There were a lot of people to coordinate, large teams that we had to, cross the divide and communicate with and get to know for the duration of the project in a very short amount of time. So how we receive the data, its accuracy and things like that, we had to work and iterate. But the lesson there was we didn't actually have to get it absolutely right. What we had to do is not get it absolutely wrong. So rather than striving for perfection, we are striving for coverage and for speed, optimizing for the hotspots of where we thought ahead of time we may encounter specific issues. So getting it absolutely right and insisting on absolute knowledge is just a dead end. So that's something we had to contend with and work with. So after we collected enough information, some key information about the source database, Mongo, but there wasn't a database. In fact, there were about 30 of them. And in fact, they divided into 5 different cluster types, cluster schemas or things used by various products spread around regions around the world. And we were going to migrate each and every one of them in different times along the project in a different region. But already there, we discovered that our wire compatibility, we had anywhere from 3.2 to 3.6, not necessarily the latest 3.6, which means applications were talking that protocol level, but also means that we didn't have, for instance, things like change streams on some of them. Some of the databases were rather small in the gigabyte range, single digit gigabytes, up to a couple of tera. Um, and then as far as logical databases, we had some that had an explosion of logical databases, which later on turned out to be a factor. So we'll talk a bit about that. So when I'm saying large scale, it's not only that we had some rather larger databases to move in a short amount of time, it's also that we had a plethora of logical databases and other, other metrics where it kind of was like, whoa, this is a lot. We might need to script around it, or we might need to babysit it extra, or worry about optimization to make things work faster. So the target database, DocumentDB, is wire compatible with 3.6. And at the time, the wire compatibility was at a certain level. What we had to watch for is what isn't. So I'll talk a little about that. Um, DocumentDB is a little different than Mongo because there is no sharded cluster there. If you do any sharding, that's client side, not infrastructure. So its scalability sources scale up. So we had to make sure that our data and workload and performance fit within the ability of DocumentDB to handle the specific workload. So the only reason for a question mark here is not because DocumentDB cannot perform. It is that it needed to perform for the specific use case, for the specific workload. So if we wanted to do a heterogeneous migration, yet keep the schema the same without major refactoring of the application, which was our charter, is not to refactor the whole application if we can. So if we wanted to keep it that way, then we had to make sure that that workload pretty much fit and was replayable against DocumentDB. So that needed to be proven. And as far as security, it had sufficient security within the networking and protocols and so forth to protect the data, so that that all actually passed in flying colors. Um, so from the outset, it seems okay. We should have a kind of a easy time because there's no real stored procedure, no storage procedures in MongoDB. There's no server-side code to translate or anything. There's no link tables or link database or anything like that. So databases are independent from each other, which means we can move them in parallel and independently. We do not have to take a whole cluster at once if we don't want to. No triggers, again, no server-side code. And there was a flexible document model. So if you're Mongo compatible, a document is just a document. You can shove it across a wire and it should just work. But there are some key differences. In the hosting, there's no sharding, and we had some sharded clusters to move, which means we needed to migrate individual shard individually into a single database. So there we had some key concerns around ID collisions, where if your ID is not just shard key, which usually is the case, you have to make sure that IDs are truly unique across a cluster. Mongo only enforces it within a shard. So we had to run some things around that to make sure that we don't have collisions. And we were lucky enough not to have them. Um, and then there is not a concern of durability in building out in the same way because of the technology of DocDB. So that was good, was actually easier to deal with because we didn't have to worry about write concerns or anything like that. On the flip side, on the write concerns, since we couldn't decrease the write concerns, we were stuck with the level of protocol that would say, yeah, you need a W1 acknowledgement, meaning that we couldn't speed up, but by just saying, hey, let's take a policy of just acknowledged or unacknowledged writes, because every write is considered a W1. So we couldn't speed up beyond that. In terms of feature coverage, our data sets, we had to do the work to compare them, but we had to ensure that all of the data types are supported. At the time, there were only small issues around data types, but we were able to get around most of them. And the data types used in the source were not anything unsupported by the target. So that was good. There were some issues around indexing, especially around um, index naming, which exceeded the target's ability, as well as we had some issues around um, the indexing of elements within an array, creating a compound index on array elements, which at the time was not supported. So that was something we needed to actually work about, go back to the source, work with the developers to identify where it was necessary and synthesize keys specifically for the use case that needed compound keys so that they are indexable. That was not a fun thing to discover, but it's something we had to do. And then finally, we had the limitations around null checks, nulls in strings. It's by now it's available in AWS, but at the time it wasn't. So we had to actually write a special tool to scan for strings that had the null character in them, which Mongo didn't have a problem with. So all of these things were preparation in order to be able to import the data into the target without performing some trace ETL or cleanup. We couldn't, we really stood no chance. So we did the work there. Okay, so with that, understanding the source and destination a little better, we started having a better vision of the game plan. We would, for D-Day, for the day of actual migration, we'd have to prepare the databases, namely quiesce as much as possible any activity on the source, just in order to make less changes needing to be updated. Um, clean the target completely, prepare any indexing, any index name shortening. We actually pre-created all the indexes in DocumentDB, which is the recommended approach for DocumentDB. Then we would perform a dump followed by a restore into DocumentDB. So dump restore rather than file copy. Why can't we do file copy in rsync? Well, because DocDB is DBAS. It's not. We have no access to its storage. And besides, the storage is not BSON. It's not nothing like a wired Tiger. So we had to do it through the wire using dump restore, Mongo dump, Mongo restore. Then we'd do some validation, and then go live. We would just switch on the applications accessing the new target, and that would be go live, or so we thought. It turns out that that dump restore go live wash cycle for many of the databases was just too long. The time window, the maintenance window during which we could do the transfer was you know small, 40 minutes or an hour or something. So we couldn't fit writing a whole terabyte or hundreds of gigabytes in that time, plus also do the testing and validation and everything within that time. So the solution there, fairly predictable. We would need to do a sync. So the idea is to do a dump restore and then follow it with all of the changes that occurred since the moment we performed the dump. So by doing that, we essentially apply all of the uplog operations from Mongo and replay it. And you could say, hey, there's change streams. That's easy. Why is he talking about it in data count? Well, some of our sources were Mongo 3.2. They didn't even have change streams. So we had to go ahead and write a special tool to do that. The idea again here is just expanding a little our process, injecting a point where we say, now we start capture the uplog timestamp for when we start the dump, then do the dump, then do the restore and replay the uplog. Anything that already got restored, playing on top of it was safe because we will get to the same picture. That's in fact what data dump and restore in Mongo does when you say replay uplog. So that allows us to shorten the cutover window. So it makes it look like we did the whole migration in the cutover window. In fact, we stole time from the past by performing the bulk of the migration in the past and fitting the rest in that window. So here we had to figure out how do we, what tool do we use? How do we actually perform the migration? Off the shelf was kind of not optimal. First of all, we needed the granular process control, and tools off the shelf either migrated one logical database at a time or required access to special operators like apply ops, that is an internal Mongo command. So those tools assume that if you're migrating Mongo, you're migrating into Mongo, or they had the kind of crusty or expensive way to migrate 1,000 databases. So those were not optimal, and relying on change streams was just not available because some of the Mongo versions we were dealing with. So we set off to write a tool, ended up writing a tool in Python. It is not open source if somebody's asking. It was done for a specific project and client, so I can't share it, but I'll describe generally how it operated. The custom tool we set to just read the uplog. So it was only made to perform the sync. It knew how to read the uplog. It would then replay each operation, each relevant operation in sequence. And that's very crucial that it has to work in sequence. It will be observable enough so that we can tell whether it's working correctly and where it's at on the whole time scale so that we fit in the time window and we can predict if it's going to catch up or not and alarm the rest of the teams if there are issues. And we also wanted to be somewhat resilient to problems, to be able to resume the work and not have to start from scratch if it didn't work. So with that, we had to deal with the entries in the uplog. The entries in the uplog range from inserts to all the CRUD operations, any data mutation and schema mutation we had to handle. So inserts would be kind of easy if inserts were only done once, but um, because we had to have it resumable, we switched them into upserts. And the reason for that is if I took the timestamp and I saved it, and then I wanted to stop the process and resume it again from a timestamp in the past, a record may already exist there. So we always wanted to be able to replay from any point of time forward all the way. And for that, we transformed the inserts into upserts that just slam the latest version in. So that linearity guaranteed that at the end we will have the right picture. And the fact that it's an upsert just laying on top of what was already there worked just fine. In terms of mutations like collection, index creation, we just skip those. One, because you can just write into a collection and it will create it behind the scenes for you. There's no hope to create the same UUID that Mongo used, and it's not important anyway. So we didn't need to have a create collection command. And indexes, if you recall, is something we pre-created. We consumed all of the indexes from the source databases and applied them in the target. The only thing we had to do here was make sure that we logged any index creation that came across, because during the sync creation, if an index creation, if during the sync period, if any index was created during that period, that's something we needed to know and apply after we finished the sync so that we can apply a new index. And those index would only occur if a new database came into the play. That's something specific to the applications and how they manage databases. So that's something we could handle easily. Drop database, drop collection, and delete were just handled as is. No need to transform it into anything special. If a record gets deleted, that's fine, document. And then the next thing we needed to do is added to the tool filtering. The idea there is we had some regions, we had a cluster that serves several regions or several targets. So from one source cluster, we multiplexed into 3 different target databases. So instead of restoring the whole database from scratch, and then removing things that weren't needed in the target database, we wanted an ability to filter based on namespace. And that actually helped us a lot because by doing that, we were able to migrate even a single collection if we wanted, um, in a single database or a single collection in a database. And that allows us to actually run things in parallel. It actually allows us to speed up the sync process by having a namespace filter and running several processes in parallel. Because MongoDB and DocumentDB do not have any joins, as long as we replay each collection in the right sequence, we are guaranteed at the end to end up with the same image of the database as the source. If we do not take it to completion, there is a chance that there will be, a user without the user profile because we sync the user all the way, but not the user profile. But if we consumed all the uplog at a point in time, we are guaranteed that all operations from the source cluster would be applied, and we can do independent collections if we wanted to. So that helped us. In terms of resumability, it was as simple as taking a timestamp and every so often writing it to a file. We didn't feel like we needed to update the file with every write because that could slow the migration process. So we did it every 100, every 1,000, every something. That was quite sufficient. So I talked a little bit about enjoying the speed from being able to parallelize and parallelization. We have to, for a single collection, you absolutely have to replay the uplog for that collection in order. But separate collections could consume the uplog and only get interested in their own collection and run in parallel. So for that, we actually had the process write a specific timestamp file for each collection that it was in charge of. And by doing that, we could run a multitude of them, and we just tuned how many processes are needed based on investigating the source and seeing how big the collections or how active those collections were, and optimizing for that. And finally, observability. The main thing there was to make sure that any problem that we encountered is visible. Um, we also needed to make sure that that the rate or the speed of the operation is observable. We needed metrics that tell us that this is about to finish or will get to finish in time. So these things were crucial. We used a combination of logging and and parameters from the OS, and also observing the rates in the ingestion point in the target, looking at the graphs there on AWS that tell us the amount of IO and how much queuing there are. Let us tune the workload and the sizing right to do things. Main thing we learned there is looking at how old an uplog item is not great, because it tells you how old it is, but it doesn't tell you how many more there are after it. So after seeing that that wasn't terribly useful in the beginning, we ended up looking at the difference in terms of how many items left and what is our current rate. So by doing this simple division, we could tell like, when do we expect to finish? That was a better predictor than only looking at how old things are. As far as error handling, we took a simple policy of the moment we see an error, we halt. The idea is instead of trying to predict ahead of time and automate the policy of what to do, we took the approach of if there's a problem, pull the cord, a human would look at it. That's also because we had a larger context of more teams to deal with that we had to consult with and have somebody take a decision on that. So if somebody has to take a decision on that, there was no real use on automating the reaction to a problem. We had to discuss it, bring it up, and come up with the proper strategy to handle it in real time. So that's easy to implement. I think I would recommend this for any ad hoc project. Automation would come later if you do it every day and you have a clear policy that is adhered to. Otherwise, you really want to involve humans. So we're kind of against time here. I have a few more slides just talking about general things that are more organizational, and then I'll take some questions. Um, because this was large scale and involved large teams, communicating what we're actually doing, what we're not doing, how we're doing it was an ongoing endeavor. We always had to explain what we're doing, put it on the table, expose every step, everything, you know, any code in source control, just make sure that everybody's clear and comfortable with what we're about to do so that nobody's coming surprised. Um, so this includes communicating the big picture of who we are, what we do, how we do it, in terms of the mechanics, code pieces, everything, and also communicate any needs we had, like we needed communication, we needed help from DBAs, we needed help accessing certain things, security, all of these things, communicate as much as possible. The partnering, I cannot stress enough, identifying the key people to work with and forming a good understanding of the vision on both sides, the needs of both sides and everything is crucial. But also making our life easier, part of it was um, communicating with the teams and removing some unnecessary craft. For example, we had one database that had close to 12,000 logical databases, and dump restore just took a long time, even though a lot of those databases were tiny. Turned out a lot of them were just test databases that were never cleaned up. So we worked with the teams responsible for those testing to inject a step to delete databases they just ad hoc use for testing and reduced it to about a tenth of the size. That alone saved us half an hour of backups and restore, which was crucial time for our time window. So things like that you discover. Uh, Measure, I think goes without saying, measure everything, investigate everything, get as much data as you can. Again, not to be perfect, but at least with the aim of not being absolutely incorrect. In a healthy amount of skepticism, we managed to discover a few instances where we actually the uplog rolled over itself, that we basically could not catch up even with parallelism. And by kind of suspecting that it might be happening and observing enough, we were able to narrow down what the cause is and perform some extra optimization ahead of time. If we wouldn't have looked at those logs and at this kind of graph of the performance, we wouldn't have found it. And early and often, that's organizational. It's not always possible, but everything we, a sense of immediacy from day one, a sense that we need it now, continuing to communicate the needs was crucial in getting to the end of the project in time. Okay, I think we're kind of done.
Please post your questions in the session Q&A so that our speaker can answer them. There's already one question. It's why doesn't MongoDB have joins?
Well, so MongoDB has a dollar lookup operator that mimics some of what join does, But joins really for relational databases are around building seemingly independent entities, tables, into joins to create a compound entity. Let's say you have a user, there's addresses, and there's user address connection with foreign keys, and that's where join is really useful. It's kind of aspect oriented. Depending on how you ask, that builds the entity on the fly. Mongo's source of scale is the ability to shard. And if you do sharding, you split your logical tables into separate nodes altogether. Um, it's very difficult to coordinate those joins because your data may be spread across your infrastructure. So for those kind of reasons, I think Mongo chose not to support joins and really to take a view of document oriented, where trivial items are joined by embedding them in the source document rather than taking a relational database approach. It's really the source of its scalability is its independence of those collections. If they try to do joins, things would be very slow very quickly.
Okay, I have a question actually. In your opinion and your experience, you chose MongoDB. Why did you go with MongoDB as instead of, let's say, going with Redis or Couchbase or Cassandra? What makes it unique for you?
This is an interesting question. I like Mongo because of its flexible data model and because of its ease of use and because of its scale and because it supports a very rich query syntax that lets me do more than just a key blob store. And some of the technologies you mentioned are a little more key blob store. Some of them have latent indexes, meaning that you can't read your own writes. So there's many reasons why I like Mongo. But in this case, and for the purpose of this talk, this choice wasn't actually ours. The client, the organization needed, had a Mongo installation. And for the step of migration, this was off the table to change technologies completely. We wanted to go to something that's cloud native. We wanted to go to something that's DBaaS, that's does not require a team of DBA to manage the infrastructure too tightly. So that was those were reasons there. But I didn't make the choice to use Mongo on this one. I totally would have though.
And we'll take the last question. Did you use MapReduce while migration to make data fetching easy?
No, not at all. MapReduce would not have helped us so much in liberating the data because we had to copy all the data. So Mongo dump was actually faster. Having BSON files on disk from the dump, from the backup step, actually helped us because we had a tool that was able to scan those BSON, those binary native files. We wrote a little tool to scan for null characters and pre-detect any issues we may encounter on restoration. So MapReduce, I don't think would have helped us there in any real way. Plus, in 3.2, there's already a aggregation framework, which is generally faster unless you have some very complex query requirements. Aggregation framework is really my way to go to do complex queries. I hardly use MapReduce these days.
Okay, so we're out of time. We'd like to thank you, Nuri, for your presentation, and we'd like to thank the attendees for joining us today. Please contact the speaker if you have any further questions regarding this topic. I hope you gained some insights from this talk. I definitely did. Please provide your comments and feedback to us, and have a wonderful day. And thank you for being part of this year's DataCon LA. Thank you, Nuri.
Thank you so much, Tala. Thanks, everybody.
Bye.